Quantum computers that are solving real problems. Executive summary. Quantum computing is no longer just a laboratory experiment. Around the world, a few companies are beginning to use quantum computers to solve real problems, from traffic and supply chain optimization to finance, energy, and materials science. Most of these uses are still in pilot or early production stages, but they show how quantum systems can already bring value to real industries. Article: Optimization and Logistics, Making Operations More Efficient. One of the areas where quantum computers are showing the most progress right now is optimization, finding the best possible arrangement or plan among many options. This could mean scheduling delivery trucks, reducing travel time, or planning the most efficient routes for workers and vehicles. D-Wave and quantum annealing. D-Wave, a company from Canada, focuses on a special kind of quantum computing called quantum annealing. Instead of using quantum gates, like a universal quantum computer, D-Wave's system searches for the lowest energy state of a mathematical landscape. That lowest point represents the most efficient or optimal solution. Retail and delivery. Save-On Foods/Pattison Food Group. D-Wave worked with Save-On Foods to automatically schedule grocery delivery drivers and plan their routes. Using D-Wave's hybrid solvers, which combine quantum and classical computing, they built a system that improves efficiency and saves time, a big deal for busy grocery operations. Traffic optimization. Volkswagen. Volkswagen ran a pilot project in Lisbon, Portugal, using D-Wave's system to calculate live bus routes based on traffic data. This project was one of the first real-world examples of a quantum-powered transportation app. Broader applications. D-Wave now reports that more companies are using its systems for scheduling, routing, and manufacturing optimization. These are early production uses, not just experiments, proof that quantum tools can already integrate into business operations. Because optimization problems are everywhere, from airline scheduling to warehouse layouts, D-Wave's approach is leading in showing measurable results today. Finance, trading, prediction, and cybersecurity. Quantum computing is also making an impact in finance, where even small improvements in speed or accuracy can mean major financial gains. IBM and HSBC, Quantum Enhanced Trading. IBM's gate model quantum computers, the more general kind that can run a wide variety of algorithms, were used in a pilot program with the global bank HSBC. The project tested a quantum algorithm for bond trading, comparing it to standard classical algorithms. The quantum approach achieved up to 34% better accuracy in predicting whether trades would be completed. That's one of the clearest demonstrations yet of quantum utility, solving a real, measurable business problem better than classical systems could. Quantinuum, quantum security and randomness. Another company, Quantinuum, focuses on quantum-safe cryptography and quantum randomness, essential for cybersecurity and financial systems. Quantum randomness means creating numbers that are truly unpredictable, which is critical for encryption. HSBC's tokenized gold pilot, HSBC, also worked with Quantinuum on a pilot that used Quantum Origin, a quantum-generated randomness service, to secure digital gold trading. This ensured that cryptographic keys were resistant to future quantum attacks, an early step toward post-quantum security. Finance is likely to be one of the first major industries to benefit from quantum technology, not only for speed, but also for improved risk management and data protection. Energy and industry, smarter grids and better batteries. Energy companies and researchers are also turning to quantum computers to improve grid management, electric vehicle charging, and battery chemistry. IonQ, trapped ion quantum systems. IonQ, based in the US, uses a technology called trapped ion quantum computing. Their systems trap ions, charged atoms, using electromagnetic fields and use laser pulses to control them. These ions make excellent qubits because they're stable and have long, coherence times, meaning they can store quantum information reliably. Oak Ridge National Laboratory IonQ partnered with Oak Ridge to demonstrate how quantum systems could help schedule power generation, a problem called unit commitment. This problem involves deciding which power plants should run at which times to meet energy demand efficiently. Hyundai IonQ also works with Hyundai to model battery chemistry for electric vehicles. Using quantum simulations, researchers hope to design better, longer-lasting batteries. Hyundai is also exploring how quantum computing might help with object detection for autonomous driving systems. Pascal, quantum forecasting for EV charging. Pascal, a French company using neutral atom quantum systems, has partnered with EDF, France's national electric utility. Their pilot project predicts electric vehicle charging demand to balance loads on the power grid. This research is part of France's GENCI program, which promotes advanced computing for energy and climate goals. Together, these projects show how quantum computing could help manage the complex, data-heavy systems that power our world. Chemistry and materials, building the future of science. Quantum computing is also opening new possibilities in chemistry and materials science, fields that depend on understanding how molecules behave at the quantum level. These simulations are often too complex for classical computers. Quantinuum, towards scalable quantum chemistry. Quantinuum has built error-corrected quantum chemistry workflows, programs that simulate molecules and chemical reactions while reducing noise and errors. These systems are still early prototypes, but already show progress toward scalable quantum chemistry. Companies like JP Morgan are using these tools in research for drug discovery and new materials. IBM, the idea of quantum utility. IBM promotes the term quantum utility, the point at which quantum computers can handle problems too complex for classical supercomputers. IBM's partners are running circuits that go beyond brute force classical methods, marking the start of true usefulness in scientific computation. These projects are still mostly pilots, but they show steady progress toward commercial reality. What solving real problems means in 2025. Quantum computing has not yet replaced classical computing, but it's starting to enhance it. Here's what that looks like today. Optimization is leading the way. Systems like D-Wave's hybrid solvers are already embedded in business workflows, scheduling drivers, planning routes, and managing resources. These are not just experiments, they're producing results companies can measure. Finance is rapidly growing. The HSBC IBM trial is one of the first cases where a quantum processor delivered a measurable business-relevant improvement. Security pilots using quantum randomness are already protecting digital assets in real workflows. Chemistry and materials are on the horizon. Quantum systems are beginning to show practical benefits for simulating molecules and materials, the foundation of drug discovery and energy innovation. These are still research efforts, but progress is accelerating as error correction improves. In short, quantum computing in 2025 is real, measurable, and industry-specific, but not yet universal. Companies are solving practical problems where quantum methods already make sense. Optimization, risk analysis, secure cryptography, and molecular simulation. What's next? Each quantum architecture, whether annealing, trapped ions, or neutral atoms, has its own strengths. D-Wave's annealing approach works well for optimization problems. Trapped ion systems from IonQ and Quantinuum are better suited for chemistry, simulation, and general-purpose quantum algorithms. Hybrid systems that mix classical and quantum computing are bridging the gap, allowing useful results even before large-scale quantum hardware is ready.